Greetings, calculus students! This lesson is part 2 of a 2-part introductory series of lessons on a concept known as integration. If you haven't watched it already, I recommend you watch integration part 1 before proceeding with this video. Recall that the velocity function v of an object moving along a one-dimensional path is the derivative of the position function s. Thus, we can refer to the position function as an antiderivative of the velocity function. Velocity is derivative of position, therefore position is antiderivative of velocity. Furthermore, recall that integrating a velocity function over an interval gives the net change in position over that interval, as summarized below. In our last lesson, we explored some velocity functions that we integrated over an interval, and the conclusions were changes in position. So it's the position at time b, or when the input variable is b, minus the position at time a, or when the input variable is a. And the key realization that connects differential and integral calculus is the fact that the derivative of s is equal to velocity. So this function s that's experiencing a change is an antiderivative of the function that is the integrand. This relationship generalizes and yields a portion of the mathematical principle known as the Fundamental Theorem of Calculus, shown below. If ever you are working with any definite integral from a to b of any function, this could be a function of t dt, the independent variable does not matter, but these coordinates must match that independent variable. In other words, this a must be an x coordinate, and this b must be an x coordinate, because that is what the differential is. In the last lesson, we learned how to approximate these definite integrals using Riemann sums, such as left-hand sums and right-hand sums. But the realization of the connection between position and velocity gives us another way to find the value of this definite integral and to find an exact value. And that would be find some antiderivative. I'll use a capital letter to represent that. So capital F must be a function such that its derivative gives you little f. And then we evaluate this by putting a bar, a on the bottom and b at the top of that bar. And this is notation to suggest that we plug b into this antiderivative and get capital F of b, and then subtract from that, plug a into this antiderivative. Thus, we can calculate any definite integral without needing to use a Riemann sum by using an antiderivative, provided it's possible to find an antiderivative of the integrand function. Now, before we explore antiderivatives a little bit, let's review the meaning of a definite integral in a few cases. For each case below, the magnitude of the area of each region is given. So this region here, between the axis and the function and over the domain from 0 to 3, has an area whose magnitude, put absolute value bars on the area, is 30. Magnitude just ensures that we have a positive response here. Now the independent variable is x, which stands for square inches, and the dependent variable, or the values of the function, or the outputs of the function, are measured in kilograms per square inch. So a definite integral from 0 to 3, and these are x coordinates, of this function will be equal to some antiderivative evaluated at 3 minus that antiderivative evaluated at 0. And in this case, this difference should match the area of the region and be positive because the function has positive values over this interval. The units on this 30 will be the units of the independent variable multiplied with the units of the dependent variable. When we do kilograms per square inch times square inches, we just get kilograms. So F represents some kind of quantity, and delta F, the change in F, is a positive 30 kilograms. Whatever F is measuring, it would be a mass, and it gained 30 kilograms. In this middle case, the area of this region is 16. This time our function is below the independent variable axis, so the outputs are all negative. The independent variable is U, standing for dollars, and the outputs G of U will have units gallons per dollar. And we're integrating between $2 and $8. So here, an integral from 2 to 8 of G of U du would be equal to some antiderivative G evaluated at 8 minus that same antiderivative evaluated at 2. And in this case, we would get a negative value because the outputs of the function are below the independent variable's axis. The units on this will be dollars times gallons per dollar. That gives us gallons, which tells us that whatever G is measuring, it decreased 16 gallons. It experienced a change of a negative value, meaning it decreased. In this last example, our function is h of t. The outputs are measured in feet per minute. The independent variable is t, measured in minutes. So this is a velocity position scenario. This area has a magnitude of 2, and this region has an area with magnitude 9. The function is above up until this t value, whatever it is, I'll call it c, and then the function has negative outputs after that. So this h of t is a velocity function. So we integrate it from t equals -1 to t equals 7. We're going to get an antiderivative, a position function, at 7 minus that antiderivative or position function at time -1. Now in this case, the result will be any regions that are above the horizontal axis will be considered a positive area, so 2, and we add to this the areas of all regions that are below, but as negative areas, -9. It perhaps makes sense to discuss area as relative area. Area is positive when it's above the axis, but negative when it's below the axis. So the end result will be a -7. This means that our position function, which is h, decreased by 7 feet because that is the product of feet per minute and minutes. Now h did not only go down over this time interval. Whatever h was at time -1, between time -1 and time c, whatever time c is, the position increased by 2. But then after time c and up to time 7, the position decreased by 9. So the overall effect between time -1 and time 7 is a decrease by 7. Okay, next page. On this page, we practice doing some antiderivatives, which we will continue to practice in later lessons. In our first example, we have a function that's 3x. We want to think of a function, capital F, such that we want the derivative of capital F to be equal to little f. Well, little f is 3x to the 1. And I know that if I do a power rule, that the power will decrease. So capital F should be some multiple of x squared. If I stop here, the derivative of capital F would be 2x, not 3x. So you got to think of some constant you would put right here so that when you do the power rule, 2 times that constant will be 3. Well, the easy way to arrive at that answer is to simply do 3 divided by 2. Now it is true, the derivative of 3/2 x squared, the 2 will drop down, multiply to the coefficient and make 3, and then the power will drop from 2 to 1, and the derivative is in fact 3x. Now this is not the only possible answer. You can also give an answer where you add any constant to this. So 3/2 x squared plus 5. Because when you differentiate this capital F, the plus 5 will go to 0, and you will still get a derivative of 3x. This suggests that if a function has an antiderivative, it does not have a unique one, because generally speaking, I can let capital F be a family of functions that have the form 3/2 x squared plus any constant, or any real number. It turns out that this represents all possible antiderivatives of little f. Next case, we want an antiderivative of a constant, so we have to think of some capital G function, where capital G prime will equal little g, and the simple answer here is to have 5x. Of course, to this, you could add any constant, such as minus radical 2. Or generally speaking, we need our antiderivatives to have the form 5x plus some constant. In this case, the power is a 2, so if I think of the power rule backwards, I know that the antiderivative had a power 3 to start. But then you have to ask yourself, what should I put right here so that when I use the power rule and the 3 multiplies to the coefficient, the result will be -2/5. Well, the easy answer is to take the coefficient that's already there and divide it by 3, which is dividing by 3 over 1, so you invert and multiply and we get -2/15. I leave it to you to confirm that the derivative of capital H will be equal to little h in this case. But then, of course, we can give any such answer, add any constant you want, such as pi, or generally speaking, capital H will be equal to -2/15 of x cubed plus any constant. Next example, m of x equals sine of x. Which function, when you differentiate it, gives you sine? Well, my thinking goes to cosine. However, the derivative of cosine is negative sine, so I need to put a negative in front of that cosine, and now I have a function whose derivative is sine. So capital M prime is equal to little m. Of course, now any function that is negative cosine of x, now you can add any constant to this to get another option, such as 11/7, or generally speaking, our family of all possible antiderivatives have the form negative cosine of x plus some constant. The next case, can you think of a function whose derivative is e to the x? This is arguably the easiest one to think about because the antiderivative, capital N of x, will be equal to itself. Sure enough, capital N prime will be little n. So e to the x plus any constant, such as plus e, would also work. Or generally speaking, e to the x plus any constant. And our last one, b of x equals 1 over x. We want to find a capital B function such that capital B prime equals little b. If you recall your derivative formulas, we need a natural log of x. The derivative of natural log of x is 1 over x. This x has only one domain restriction. It can't be 0. It can be positive or negative. But this x has to only be positive. And so we don't want to find an antiderivative that has a much smaller domain. A way to fix this in this case is to put this x in absolute value, because now the only restriction is that x can't be 0. And also the derivative of natural log of absolute value of x is still 1 over x, as discussed in earlier lectures. So b of x equals natural log of absolute x plus any constant you want, such as subtracting 0.1. And generally speaking, b of x would be the natural log of x plus any constant, positive, negative, or 0. Okay, let's move on back to the context of definite integrals on the next page. In particular, we revisit scenario 1 from the previous lesson. Now, scenario 1 was a situation where we had the velocity of an accelerating runner in feet per second as a function of the number of seconds is v of t equals 0.1 times t squared plus 4, whose graph is below for t between 0 and 6. Use the fundamental theorem to confirm the exact distance traveled in the first 6 seconds. Well, the definite integral that we want to set up is an integral from 0 to 6, the velocity function, which is 0.1 t squared plus 4, and then a differential, and it should be dt in this case, because we have a t-axis, and these are t-coordinates, and t is the independent variable. And your differential must match. Everything here must be with respect to t. The vertical axis here is velocity, and this velocity function is above the horizontal axis, so we are looking for the exact area of this region. Now, if I use technology, in Desmos, type in int for integral. We're integrating from 0 up to 6. Use parentheses for the integrand, 0.1 t squared plus 4, and then dt. And the answer we get is 31.2, or in fraction form, 156 fifths. And what would be the unit on this? T is measured in seconds, velocity is measured in feet per second. So when you multiply these units as you would for area, you would get feet. So this is a case where area does not represent area. We're using area to represent a distance. Furthermore, this is the change in position over the interval from t equals 0 to t equals 6. So the runner gained 31.2 feet during the first 6 seconds of running. I invite you to compare this answer with the approximations we got in the last lesson. But now I want to show how the fundamental theorem is the tool whereby we get this answer. So we begin with our integral from 0 to 6. I'm going to change 0.1 to a fraction 1/10 of t squared plus 4 dt. The first thing I want to do is find an antiderivative of 1/10 t squared plus 4. And I can antidifferentiate term by term. Let's focus on this t squared. I would have to increase that power up to cube. And then I have to come up with what number it needs to be here so that the derivative will work out. Well, because when I differentiate t cubed, this cube will drop and multiply to the coefficient, I need to put here a number that is 1/3 of this number. So if I take 1/10 and divide by 3, I get 1/30. And then the antiderivative of 4 will go to 4t. Now, the next question is, what value constant can or should I put here when I calculate my antiderivative? It turns out that it doesn't matter what constant you put there, because when you do the subtraction, it'll cancel. For example, let's put a plus 1. This is an antiderivative of the integrand, and now I'm going to evaluate it from 0 to 6. Plug 6 in here. We'll have a 6 cubed over 30. Well, one of the 6's will cancel with a 30, leaving a 5. So we have 6 squared over 5. So 36 fifths plus, now plug 6 into 4t. We get 24, and then we have that plus 1. Put this all in parentheses, subtract, start new parentheses. And now plug in 0. Well, 0 goes in here, and 0 is out. 0 goes in here, and 0 is out. So all you have is this plus 1. So this will become minus 1. And now when I simplify this, you'll see that it didn't matter what constant I put here because it gets canceled when I do the subtraction. So my answer will be 36 fifths plus 24. Well, 24 is 120 fifths. And when you combine these, you do in fact get 156 fifths, confirming what technology gives us. In general, when you're using the fundamental theorem to find the value of a definite integral, just choose this constant to be 0. It won't matter what constant you put there because it will cancel, so might as well just not put it there at all. Okay, next page. Now we revisit scenario 2 from the previous lesson. Scenario 2 was that a car is initially 1 mile to the right of a house. The velocity in miles per minute as a function of the number of minutes is v of t equals negative 0.1 t squared plus 1.6, whose graph is below for t between 0 and 6. Furthermore, when v is positive, the car is moving right, and when v is negative, the car is moving left. I'm going to keep track of a diagram of where the car is relative to the house, and we will say that this corresponds to the position being 0. So initially, the car is 1 mile to the right of a house. So when t is 0, our position is 1, meaning 1 mile, and positive, meaning to the right. Now on our graph, the horizontal axis is time, measured in minutes, and the vertical axis is velocity, measured in miles per minute. For time between 0 and 4, the velocity is positive, so the car will be moving right. Then it's at rest at time 4, and then between time 4 and time 6, the velocity is negative, meaning the car is moving to the left. Well, the amount of distance that it moves to the right corresponds to the amount of area under this portion of the velocity curve. And we can find that using the fundamental theorem. So we want to integrate from 0 to 4. The velocity function is negative 1/10 t squared plus 1.6, and then dt. So we find an antiderivative. This will be similar to what we just did. The antiderivative will be negative 1/30 t cubed plus 1.6 t. And this time I'll choose the arbitrary constant to be 0. And then I'll end the parentheses, put a vertical line, and evaluate from 0 to 4. And we plug in the 4 first. Well, 4 times 4 times 4 is 64. 64 over 30 simplifies to 32 over 15. Plus, these 1.6's I'll convert to fractions. It's 16/10 or 8/5. Now let's plug 4 in for t here, and we get 32/5. And this is what we get when we plug 4 in. Now we say minus, and now we plug in 0. But when you plug in 0, we just get 0 plus 0. Now we need a common denominator. We have negative 32/15 plus 96/15, and that gives me 64/15, which is about 4.267. And the units would be minutes times miles per minute, which gives us miles. So this area tells us that the change in position is 64/15 miles. And I'll use this fraction and not the decimal. And the change in position is positive, suggesting that we are going further to the right. S is increasing. So we want to go to the right, 64/15. And at time 4 minutes, our new position will be 1 plus 64/15. Get a common denominator, and that gives us 79/15. That's how far the car is from the house and to the right at this time. Now we want to find the definite integral, but from 4 to 6 of our velocity function. I expect a negative answer here because the outputs are negative. We've already anti-differentiated, so negative 1/30 t cubed plus 8/5 t. Evaluated this time, though, from 4 to 6. So plugging in 6 cubed, well, one of those 6's cancels with the 30, leaving a 5. So we have negative 36/5 plus 48/5. Put that in parentheses, minus, start new parentheses, and now plug in 4. So 4 goes in to this antiderivative, but we've already done that up here, and we got this result, which simplified to this fraction. So I'll borrow that work and just put my 64/15 here. So we get 12/5 minus 64/15. Get a common denominator, and in the end we get negative 28/15, measured in miles. This suggests that our delta S for this time interval is negative 28/15 miles, suggesting that we are now going to the left. S is decreasing by 28/15, putting me at a final location when t equals 6, and that location is S equals, and we take this position and then subtract 28/15. That gives me 51/15. And this would be the position of the car at the 6-minute mark, still to the right of the house. Question 2 is use the fundamental theorem to confirm the exact change in position from 0 to 6 minutes. Since I'm running low on space, I'll use technology and put that integral up here. So integrate from 0 to 6. Using technology, we get 12/5. This suggests that the net change in position over the entire first 6 minutes was simply 12/5 miles. And it's positive, meaning we gained 12/5 miles from where we started. So our position at time 6 would be our position at time 0 plus this integral that we just calculated. And we get 1 plus 12/5, which is 17/5. I should note that our 51/15 we had over here, that I neglected to simplify this, 51/15, both numbers are divisible by 3, So our position at time 6, according to this analysis, is also 17/5. And this would be measured in miles, and we are right of the house. And question 4 is determine the total distance the car traveled in the first 6 minutes. If we integrate from 0 to 6, we get 12/5. But this does not mean the car traveled 12/5 miles, because it did some backtracking. Even though the car finished 12/5 miles away from where it started, its total distance is actually more. The total distance can be found by finding how far it went right and then adding to that how far it went left. So if you find the absolute value of our answers, if we take the absolute value of the integral from 0 to 4 of the velocity and add to that the absolute value of the integral from 4 to 6 of the velocity, so take this distance it went right and then make this distance be positive and then add them together, we can get the total distance traveled. So we get 64/15 and add to that 28/15, and we get 92/15 measured in miles. Okay, there's a lot of information on this page. We color code. The answers to question 1 are these two answers. Question 2 was answered here with units of miles. Question 3 was answered here, that the car at the 6-minute mark was 17/5 miles right of the house. And question 4 was answered here, that the total distance traveled was 92/15 miles. Okay, next page. In some cases, a definite integral can be computed using geometric formulas for area. Use both geometric formulas and the fundamental theorem of calculus to calculate each definite integral given the graph of the function. Well, this function is linear, so we will want to find its equation. We can clearly see the y-intercept is 1, and we have a slope of rise over run of -1/2. So I can go straight to mx plus b form and say -1/2 x plus 1. Now the first integral is from -2 to 2. Over that window, the function is positive above the x-axis. So we want the area of this triangle, effectively. And I don't need to use calculus to find it, nor do I need to use a Riemann sum to approximate it, because the shape ultimately is geometric, a right triangle whose area I can find. The height is 2. We can see that the base is 4. So we do 1/2 base times height, which gives me a total area of 4. Now there are no units given here, so I can't put a unit on this 4. Let's confirm that we get 4 by using the fundamental theorem, because I now know what the function is. It's -1/2 x plus 1. We want to find an antiderivative of this. So the x will go to x squared, and I need to now divide the coefficient by 2. So we'll get -1/4 x squared, and then the antiderivative of 1 is x. So here's my antiderivative. We will evaluate from -2 to 2. Plug in a 2 first. We get 2 squared over 4, so we have a -1, and then plus a 2. Put that in parentheses, subtract, start parentheses, and now plug in -2. Well, -2 squared is still positive 4, so I get a -1 still, but then minus a 2. So we get a positive 1 in the first parentheses minus, and a -3 in the second parentheses, and so we get a final result of 4, confirming our answer we got via the area formula for a triangle. Now in this next interval, from 4 to 6, that's this portion of the function, it is below the x-axis, so I expect my answer to be a negative number, the magnitude of which would equal this area exactly. We can split this into 2 regions, split it there. I see a rectangle and a triangle. The rectangle is 2 by 1. The triangle is also 2 by 1, but cut that in half. So the rectangle is area 2, and the triangle is area 1. So I expect an area of 3, but negative because we're below the x-axis. Let's confirm with the fundamental theorem. We're integrating from 4 to 6 of this function. We've already given the antiderivative of -1/4 x squared plus x. Evaluate this time from 4 to 6. Plug in 6 first. 6 squared is 36. Divide by 4 is 9. So we have -9, and then plus a 6. Put that in parentheses, minus parentheses. Now plug the 4 in to the antiderivative. 4 squared is 16. Divide by 4 is 4. That negative in front, so we have -4, and then plus a 4. Well, that zeroes out, and the first portion gives us -3, confirming our answer. One more to do. We're integrating from 0 to 6. Well, for part of this interval, the function's above, and for part, it's below. So I'll redraw this portion so I don't clutter the other picture. We're starting at 0. The intercept is at 2, and we're integrating up to 6. In this case, we're going to get some offsetting areas. This area will be positive. This area will be negative. Orange triangle is 2 by 1. So the magnitude of the area here is 1/2 base times height. So we get an area of 1. The red triangle is 4 by 2. We use half base times height, and we get a magnitude of 4 for that area. So when I do this integral, I expect a positive 1 to be combined with a -4, and I expected -3 again. Let's confirm with the fundamental theorem. Integrate from 0 to 6, this function. We've already found the antiderivative, so -1/4 x squared plus x, and then evaluate from 0 to 6. We plug in 6 first, and once again I'll get -9 plus 6, and then minus, and when I plug in 0, I'll just get clearly 0. So once again, I do confirm a -3 answer. So we see that there can be options for finding the value of a definite integral, especially if the regions have shapes that are geometric, such as circles or portions of circles, triangles, rectangles, or combinations of those shapes, such as trapezoids. All right, moving on to the last page. The following properties hold true for definite integrals. If you integrate some constant from a to b, then we can confirm what this will give us using the fundamental theorem. The antiderivative of a constant and treating x as the independent variable, as revealed by the differential, we will get that constant times x. And then we evaluate from a to b. So we plug in b first, subtract, and now we plug in a. Or we can factor the k out and say, integrating a constant from a to b will always be the constant times the difference b minus a. Here, a definite integral of a function plus or minus another function. You can split up the integral into two and do a definite integral of just the first function, and then plus or minus, whatever the sign was, a definite integral of the second function. And you can approach these integrals separately and maybe using different techniques on the different parts. This next property, if you have a constant times a function, as your integrand, you can actually factor that constant outside of the definite integral, simplifying your integrand to just f of x, and then evaluate the definite integral without the k. But then remember to multiply your final answer by k. This next one, notice that we're integrating from a to a. Think of what that means visually. You have some function, the axis, and you're integrating from a to a again. So you're finding the area between a and a, but you wouldn't be able to. It would have a 0 area. So it makes sense that this answer would be 0. It also makes sense that if you use the fundamental theorem and you find some capital F function and evaluate it at a and then remove the same capital F function evaluated at a again, these would cancel each other and you would just get 0. This next property, if you integrate from a to b, you can actually reverse the order of the integration. Put the b as the lower limit and the a as the upper limit, and then integrate the function. If you do this, however, a negative is generated. So whatever answer you get for this definite integral, you would have to multiply by -1, and that would be the answer you would get for this integral. This next property, if you integrate from a to b some function, imagine a simple picture where the function's above the x-axis, that the area between the function and the axis here can be broken up into two pieces. You can put some c between a and b somewhere, and then find this area, and then find the other area and add them together. In other words, you can always sort of cut an integral by some number and split this into two. The first integral will be from a to c, f of x dx, plus, and then the second integral will complete from c to b, f of x dx. Look at this property backwards. If you integrate from a to c of a function, and then you add to that the same function integrated, picking up again at c to b, you can collapse this into a single integral that you see right here. Now, it turns out that c doesn't even have to be in between a and b, and this will still be a true property. In fact, b does not even have to be bigger than a. It's possible to do an integral, say from 3 to 6, and then you can also integrate instead from 6 to 3. Now combine the following expression into one definite integral. Currently there are 3. All of the integrands are the same, g of x, so it may be possible to do as instructed here. The first thing I notice is that we have subtraction, so I'm going to use the property where I effectively absorb that subtraction into this integral and reverse its limits and change the operation to addition. So we have an integral from 1 to 2 of g, I'll leave off the of x, and now we have plus an integral from 2 to 3 of g dx, and then we have the third integral from 3 to 0 of g. Well, looking at the first two, the first one ends at 2 and starts at 2, so I can collapse these together into one integral and integrate from 1 to 3 instead, g dx, plus an integral from 3 to 0, g dx. Well, I see this happening again. The first integral ends at 3, and the second one begins at 3. So I can collapse these yet again into an integral from just 1 to 0, g dx. And if I don't like the fact that 0 is a smaller number, but it's the upper limit of integration, then you are welcome to flip this around and put 0 back at the bottom of the integral with 1 at the top, as long as you produce a negative in the process. Okay, and this concludes our part 2 lesson on integration.